elementary school, but then I moved out to Shallow for middle and high school.
Did you play any sports at Schovanec?
Yeah, I ran cross country. Freshman year, I did volleyball and track and basketball, and then
I got you
The water's up here.
I don't know,
Where'd you
maybe I
go?
haven't.
Those are to clean the board.
I went to Seminole.
oh, okay,
Not.
that's cool.
Okay, last time we compared these two integrals, but I had a 1/2 power. Let's change it to 1/3 so that this is defined everywhere. The common trait that these two integrals have is that they have a huge discontinuity when x is 2. And when x is 2, I'm within the limits of integration. So this is from section, let's make up a number. 10.7?
Yeah.
10.7. These are both called improper integrals, and I said they are of the type 2 variety. This is a type 2, according to your text. Improper integral. Involves something of the form, the integral from a to b of f of x dx, in which f is not defined at a or at b or at some point within the interval from A to B. But there's a discontinuity. In either case, direct computation of the integral is not allowed. That's only the fundamental theorem of calculus applies to functions that are continuous all over the interval, including the two endpoints. This integral on the right is going to converge. In other words, it'll have a finite value doing legitimate steps. And the integral on the left is going to be an infinite integral. It's going to take on a value of infinity. This integral will diverge. In other words, it will be infinite. And this one will converge. But we don't know that until we attempt to compute them. And what we're going to do to both of them is look at the discontinuity over the interval from 1 to 3, which occurs at x is equal to 2. We're going to pick numbers real close to 2. We'll actually just let them be letters real close to 2. We're going to change our integral so that we're going to, what did I use, A's and B's? I think I put a B here and an A there. And then we're going to take B going to 2 from the left and A going to 2 from the right. We're going to compute the antiderivatives in terms of the functions or the variables A and B, and then take those functions of A and B. And if the limit exists, then that value will contribute to the integral. If the limit doesn't exist, becomes infinite, then the integral itself is going to diverge. So we first start by rewriting each integral. I'm going to write this as the integral from 1 to 2. Added to the integral from 2 to 3. And then I'm going to put those A's and B's here. B is going to 2 from the left, so I'm going to put the B up there. And take the limit of this. This B goes to 2 from the left. And then here I'm going to replace that 2 with a and let a go to 2 from the right. And now these integrals do fit the criteria for me to be able to calculate an antiderivative and evaluate it at the endpoints. So we're going to integrate them both as u to the minus 2. What's the integral of u to the minus 2?
-1/u.
Both of those have the same antiderivative of a -1 over x minus 2. Keep this limit following me along. -1 over x minus 2, evaluated from 1 to b. And we do it out here. Come back and get this one in a minute, but let's finish the calculations for this one. Take that up here. I'm going to put the b in and the 1 in and look at that expression. I'm going to have -1 over b minus 2. Then I subtract, but when I subtract something that's negative, it'll just put a plus right here. And then I'm going to put the 1 in. Got the limit. As a goes to 2 from the right. Put the 3 in. Minus and minus is going to again give me a plus here. And then I'll have a minus 2. Then give you a second to take a look at what you've just written down and tell me why I say that this integral is going to diverge.
Because if you sub in 2 for a and b, you're gonna get 1/0.
Right. As this b is still in the denominator, it's still a b minus 2. So when b gets close to 2, this gets close to 0. So this thing goes to infinity. So this limit does not exist. Neither does that one. And that's so when the limit does not exist, we say or when the limit is infinite or does not exist, we say the integral diverges. Does not exist. There's my abbreviation for does not exist. We say the integral diverges. So changing the exponent to a 1/3 makes the exponent small enough so that when I do this, tell me what you get when you integrate u to the minus 1/3.
Positive 2/3, so three halves.
3 halves u to the 2/3. So my u term, which houses the x minus 2, is not going to be in the denominator. So those limits are going to exist this time. Let's put all the steps in here with all of their glory. I'm going to erase that so that I have room to put it. But it'll be at this stage in the game where my x minus 2 now is going to be in the numerator, and these limits are going to exist. So we start the same way. This goes here, and this goes here, but make the exponents into a 1/3. So for this one, gonna change the exponents here to a 1/3. Start the same way. Make these exponents 1/3. It's this line that's gonna change right here. Continue with my limit, b is going to go to 2 from the left. And I said when I integrate that, I get 3/2. U is x minus 2, 2/3 power, to be evaluated from 1 to b. And then I get the limit as a goes to 2 from the right. Same antiderivative, 3/2, x minus 2 to the 2/3 from a to 3. Yes, sir.
So if what we're gonna substitute is on the bottom, the only time, or in this case, anytime we do have a whole, if the exponent on that entire part is less than 1, then it's gonna convert.
Should work out the same way.
Like,
If it's smaller than 1, it's gonna end up back on the top.
so can we use that as kind of a rule?
Kind of a rule, but they're not all gonna be polynomial type things, so I can throw some other functions in here. Okay? But that's absolutely true. All right, so I'm gonna put the b in here. So I have 3/2, b minus 2 to the 2/3. And then when I put the 1 in there, I get a -1 to the 2/3. That's a cube root that's squared. So when I put that 1 in here and have a -1 to the 2/3, what's that value gonna be?
1.
That's gonna be 1, right? Cube root of -1 is -1, and then square that gives me 1. So this is just gonna be 3/2 here. But then let me go ahead and do the next part. So we have a 3/2, 3 minus 2 is 1. So I'm not gonna write that. And then a minus 2 to the 2/3. Okay, so this limit does exist. What is the limit here when b goes to 2? 0. So this is gonna be 0. This is gonna be 1, so I'm gonna get a -3/2. Then I get plus 3/2. And then this limit's gonna be 0. So my integral converges, and it converges to 0. So you're right, we needed this limit to exist. So we needed this exponent small enough that when we do the integration step of adding 1 to the power and dividing by the new power, that this ends up as a positive exponent. So that's what I had intended to do with that -1/2 power, but dang it. Forgot about the fact that square roots of negative numbers weren't defined.
Only a minor detail.
It happened exactly on Friday. Now, what we have is some sort of vertical asymptote here, and we need our function to get close enough to it. The first case, it wasn't close enough. But when I had a 1/3 power, it was. So we need this. And what do we mean by close enough? I don't know. We'll just have to see close enough that those limits exist. Okay, sometimes they squeeze real tight, sometimes they don't. This one had some negative area and positive area, so it was symmetric to the x-axis. So let's try another one. Determine whether improper integral converges, diverges, and if it converges, find its value. What makes this integral improper to begin with?
Yeah.
It's not defined when x is 1, right? This is not defined when x is 1, so it's improper. As the integrand is not defined when x is 1.
Isn't it also imaginary at like X
Yeah,
is 2?
then it's negative under the root.
Anything greater than
Okay, let me swap it. Okay, so I had the same problem twice. Is that so bad? That I keep making the same mistake twice from 0 to 1? Not defined.
Twice is okay, but any more than twice.
You make 3 mistakes.
Time.
The third time, boo.
The third time you end
She
class.
just call me dummy in public.
I believe that counts as losing your degree.
No, it's just
No,
that
it's
if
just
you
the class
make
ends.
3 mistakes, then you end class.
That has to be in the same class. They don't carry over from one week to the next. They expire.
We're carrying the one this time.
We're carrying it over because you make very few.
I will not allow the inmates to run the asylum. I am the keeper of the asylum. The head crazy lady. Okay, so this bad boy is undefined at x is equal to 1, but defined everywhere else. So we don't have to split it apart. We'll just put a dummy variable up there where the 1 is.
Oh, yeah.
Right? Because this time it's a limit of the integral. So we're going to write this instead with a limit. Pick your favorite letter and put it up there. I always put b's as the upper limit and a's as the lower limit. So I'm going to let b go to 1 from 0 to b. I'm coming in from the 0 side, so technically this is a left-hand limit. That's not a UDU integral, is it? It's an arc sine integral. They recognize that? A squared minus x squared. So a is 1, so I should just get the arc sine of x. Zero to b. What's the arc sine of 0?
It should be 0.
It is 0 because the sine of the angle 0 gives us 0. Right, so this number here is 0. This approaches the arc sine of 1. Is there an angle that we take the sine of to get 1?
Pi over 2.
Pi over 2? So this integral converges, and it converges to pi over 2.
What would that look like on a graph? Like converges on a point. How does that?
It converges over that interval
Okay.
to that value. In other words, this thing encompasses an area of pi over 2 square units, even though that left end is left or the right end is unbounded. So let me see roughly what the graph looks like. Here is x is equal to 1. At 0, this is at 1. And then what? It's not defined anywhere beyond that. It's going to be decreasing. And then you guys told me there's not any value beyond here. So whatever's happening in here,
It's a super tight
it's getting
parabola.
real tight to that.
Okay.
It looks
As
like
it,
that.
as it approaches 1, the graph increases.
As it
Because
approaches
the
1, that's right, the
denominator-
graph does increase.
It's asymptotically.
Because that, I put my 1 on the wrong side. Let's make that 1, and it's doing that,
But way tighter.
but way tighter, but I can't draw it tight for everybody to see. All right, so it gets tight enough that this becomes pi over 2 square units of area right in here, even though that this never really hits that line.
So you get a line, an infinitesimally thin line that's infinity. So it like, that infinity is canceled by an infinitely thin.
Canceled, it just doesn't, it doesn't contribute. You think of an integral as a sum. So essentially you're adding a bunch of zeros at the end. You're looking at area that's a real thin line.
Got so many decimals,
So many
so many
decimals.
zeros behind the decimal.
It's really long, but it's.
That's right, it's an unbounded region that has finite area.
So weird.
Is it an approximation?
It's exact. It's exact, because the limit exists.
Never technically a 0, 'cause it just keeps like
No.
getting split in half, so like
Down the other one here for you.
technically, you still got some length, you know? Never just Stindo.
Yeah, last.
Let's try. Let's look at this one. Is that integral improper?
One is 0, right?
Well, the natural log of 1 is defined. Natural log of 1 is 0. Natural log of 0 is not defined.
You never.
Right? So natural log of x is not defined, and x is 0. So we're going to make this an integral with a limit there. Right? The log of x looks something like this. Here's x is 1. So what we're looking for is what's going on in here. Is that infinitely large, or is that going to be some finite number?
So we should expect a negative area.
A negative value for this interval, yes. We're going to rewrite that. Not the 0. Whatever letter you want. Again, I like to use A's as the lower limit and B's as the upper limit. Let's just do the indefinite integral first. How do you do that integral?
It's gonna be XL and X minus X.
Oh, you got that one memorized, huh?
I do my flashcards every night. I'm
Yeah,
getting so
baby.
fast.
Let's go see why that is. How does that, where did that formula come from? So I want you to compute this integral by integration by parts. Those of you who haven't memorized that integral. Do integration by parts and see if you can come up with the value or the antiderivative.
You don't have to say that you're going from.
I'm just gonna do the, oh yeah, I should do right. Right, because I'm coming in from the right-hand side?
There is no, it's impossible to approach from the left, right?
Correct. Oh, I'm coming in from the left. I'm coming in from the one side.
No, you're
I'm
right,
coming in
right.
from the right. I am. Read my picture.
You have to.
I want everybody to make sure you can compute this integral with integration by parts. Since you don't know how to integrate natural log of x, that's u, and dv is the dx. U is log of x, dv is dx, and you need ub minus the integral of v du.
With integration by parts, you still keep the numbers on the integral.
Yeah, I was just doing it without the numbers, just for the, put it up here later. So if u is the natural log of x and dv is dx, and du was 1 over x, and v is x. And so my uv is going to look like x ln of x minus the integral of v times du. So the x times the 1 over x cancels to 1. And so we get x ln x minus 1. Oops,
X.
integral of 1. Integral of 1 dx. And x ln of x minus x. So we're going to take that and evaluate it from a to 1. So we have x ln x minus x from a to 1 with the limit as x a goes to 0 from the right.
So this still has the ln, so. Oh, wait.
All right, so I'm putting the 1 in there. 1 times the natural log of 1 minus 1. Now I'm going to put the a in there. A times the natural log of a minus a. What's the natural log of 1? 0. So this just gives me -1 here. I forgot my limit, so let me put it here. So what's happening?
It's still diverging.
This is going to 0. This behaves like 0 times infinity. 0 times infinity isn't necessarily 0. 0 times infinity is an indeterminate form.
I thought about this in the shower a lot. I don't see why.
Same.
Infinity is 0.
Yeah, I don't see why you're thinking about it in the shower either.
No. Why is it indeterminate? Because infinity zeros is just 0 plus 0 plus 0 plus 0 plus 0. An infinite number of times you can get 0. And 0 infinities is no infinity.
Whoa.
I don't get it either.
Right, multiplication is
But I trust
basically adding that many times.
So these are both indeterminate.
like themes.
Sure.
Why are those so obviously indeterminate?
Because you don't know the value of infinity, so
Right?
You
I don't
can't
know
divide
the
it by-
value of the infinity. I don't know the value of the 0 either. It's close to 0.
yeah.
They're both close. They're not
Okay.
necessarily 0. That's the form that it's in, but it's not multiplying 0 times infinity. Numbers close to 0 multiplied with numbers that are really large.
Makes sense.
Yeah.
So this is just an approximation of 0.
It's a limit. It's a limit.
Okay.
Right? So this has an indeterminate form here, so we got to figure it out. If I can put it in one of these forms, I can do L'Hopital's rule,
Ah, yes.
right? So how about I do that? I got room right here. So I'm really working on this limit right here. It's the x ln of x that we're worried about, right? Because this goes to 0. So this is going to 0 and that's going to infinity. So what was the trick of taking it out of this form to put it in one of these two forms? Who remembers? Can't take a derivative until I get it in one of these forms. I'm trying to use L'Hopital's rule. But I don't have it in the right form yet.
Multiply by infinity on top of
Is it like multiply by 1 or something? 1.
Kind of. I'm gonna do this and you tell me why it's illegal in every state except for maybe Arkansas.
Well, everything's illegal in Arkansas.
Because Arkansas, they wouldn't have a clue. What I just do?
You just rewrote it as.
Yeah. But it's the same, right? As long as, I need my A in here. Need my A. I'm evaluating it at A. Multiplying by A is the same as dividing by 1 over A, but now I have it in the right form. This is infinite and this is infinite, the right form to use L'Hopital's rule. So I take the derivative of the top and divide it by the derivative of the bottom. Here the top is 1 over A. What's the derivative of the bottom? What's the derivative of 1 over A with respect to A? What's the derivative of 1 over X?
1 over a squared.
Negative 1 over A squared. So when I divide this one by that one, then I flip that one over and multiply.
A.
So I've got a 1 over A times a negative A squared over 1. So this becomes the limit as A goes to 0 from the right of a negative A. My gosh, that limit exists and is 0. So in other words, here I am, this becomes, let me rub that out. This becomes 0 and A was going to 0, so that's 0. And so this limit does exist. And so this integral converges to -1. Okay, the type 2 improper integrals are the ones that take all the room. The ones that are easy to do are the type 1 improper integrals. And those are the type when the limits on the integral sign become infinite. Let's look at those now. Type 1 improper integral.
I really despise the backwards.
I do the one that I don't like first, and then the type one that I like, I can spend more time on. Instead, I run the asylum.
Most of them were
Slumpies,
extremely,
right, circles,
extremely abusive.
actually. That's an interesting way to say classroom. We might be-
Type 1 improper integral looks like this.
Terrible.
Or this. Or this. Or F is continuous on the bounds. Where F is continuous on the interval from a to infinity, or in the other cases, minus infinity to b, or minus infinity to infinity, depending on which case we're looking at of case 1. So these two examples pop to my mind. Integral from 1 to infinity of 1 over x. Compare that to the integral from 1 to infinity of 1 over x squared. Shapes of their graph are very similar. Both of these are shaped like hyperbolas. One like this. And I'm looking at whether or not the area under the curve on out to infinity is a finite number or an infinite number. If it's a finite number, then the integral converges. If it's infinite, then the integral diverges. One of these converges, one of them diverges. And the way we figure that out is very similar to the way we did it a second ago. We just kind of make it a proper integral. We're going to stop our integral out here at some big number. I'll use a big N. I'm going to find the area from 1 to n, and then I'm going to let n go to infinity. So let's do both of these the same way. Let's look at the limit. As n goes to infinity of the integral from 1 to n. And then we'll do it over here as well. So let me see if you can finish those two up and tell me which of these converges and which diverges. Or do they both diverge?
I think the first one diverges.
The first one definitely diverges because that's a logarithm. Right, a logarithm is a growing function. This is the natural log of x from 1 to n, with the limit as n goes to infinity. So we're looking at the limit as n goes to infinity of the natural log of n. The natural log of 1 is 0. Logarithm is a growing function, so even if it grows slowly, as this gets big, so does that. So this integral diverges.
I think the
Yeah, the
second
second one
one
converges.
converges
Second one
at
converges. What's the antiderivative of 1 over x squared?
negative 1 over x.
Good. Now we look at the limit as n goes to infinity. Negative 1 over n minus a negative 1 over 1. So as n goes to infinity, this first fraction goes to 0, doesn't it? So not only does this converge, it converges to 1. The total area under this curve from 1 to infinity is 1 square unit of area. But under this one, it's infinite. The only difference is a factor of 2. 1 over x squared hugs it half as tall toward the end. So isn't that cool that you can have an infinite region, whether it's this way or that way, that has a finite area? If it's tight enough. If it's tight enough to either the vertical or the horizontal asymptote. So in the other example, when we had a discontinuity down here, the smaller power made it converge. What if I looked at this and ask you, what does P have to be for this integral to converge?
Greater than 1.
For what P does this converge?
Made it greater than 1.
We would need it greater than 1, wouldn't we? We saw when it was equal to 1, it didn't converge. If say this were a half, then I'm integrating x to the negative 1/2. Add 1 to the negative 1/2, it's going to put it in the numerator, right? You need it small enough so that when you move it up and add 1, it still has a negative power. So in this case, it converges only if that power is strictly bigger than 1.
So is that specifically just for type 1?
For this, when one of the limits is infinite. Something. Okay, so converge or diverge. Let's look at the integral. So minus infinity. I don't know. 1 of e to the 2x. So e to the x is a continuous function. It grows real quick. It's the minus infinity that makes this improper. Take a minute and state that it's improper because this lower limit. And decide. This little letter right there and let n go to minus infinity. Right? Put that step in. Skip that step, then you're acting like a regular calculus student. You guys are honors. You're going to put the right mathematical steps in. All right, now you're going to compute the antiderivative. What's the
Are you fine with
antiderivative?
us using like A instead of
You can
A?
use whatever letter you like. All right, so what's the integral of e to the 2x?
1/2 e to the 2x.
1/2 e to the 2x. All right, so I get 1/2. Let's see, that'll be e squared minus e to the 2n. So e squared's a nice number. Now n is going to minus infinity. So 2 times minus infinity is going to minus infinity. So what's the behavior of e to the minus infinity? Make up your mind.
Which is 0. I'll say it.
Yeah, if you have a negative exponent, you can think of that as, this is my cloud in my head. Right? Move it down. E to the infinity gets big real fast, divide that into 1, poof, it's gone. And so this is going to 0. So this converges to 1/2 e squared. Or you can think that e to the minus infinity, if this is the graph of e to the x, right? As x goes to minus infinity, e to the x goes to 0. But as x goes to plus infinity, e to the x itself goes to infinity. What about the logarithm? What if I put our logarithm back up here? And let's integrate the natural log of x from 1 to infinity. Was the antiderivative of the natural log of x?
That's all you guys.
X ln x minus 1.
Minus X.
Minus x. Oh,
Come on.
That's the mistake today. Let's go. One more.
She already made that.
You got 30 minutes to not make a mistake.
I got this. No pressure.
Give me 10.
All right. Just knowing the shape of the log graph, this doesn't have a chance in heck of converging, does it?
Right.
Because what we need is the asymptotic behavior at minus infinity or infinity. And the logarithm doesn't have asymptotic behavior toward infinity, does it? It continues to grow. So that's what you're going to see here. Just a little spoiler alert.
I thought we were gonna get like a plot twist based on the way you're phrasing that. But I shouldn't.
And then when I put a 1 in there, that's 0, and that's a minus 1. Well, there's kind of a plot twist, because this is infinity minus infinity, which is another indeterminate form. We can fix it. We can factor out the n. Right, that is the natural log of n minus 1. And now it's infinity times infinity. And now it's infinite.
Like that.
We gotta add the 1 on the end too, don't we?
Oh, well, plus 1.
Plus C.
So this integral diverges. So again, you need asymptotic behavior. What this is showing you is that this area is infinite. Well, duh. Right? You needed to start hugging things real tight.
So is infinity the answer, or is it just?
It diverges.
Okay.
Infinity is the answer. It's infinite areas with
Infinity is
infinity.
the answer to everything.
So
It's a fire.
Although
It's not a
outside
drill.
math.
if there was just like a horizontal line, that would be an area of infinite.
Horizontal line has No area, right? What's the integral from a to a of f of x dx?
That's vertical, that's vertical. That's vertical.
Oh, yeah, the integral say from 1 to infinity of 4. So that's a rectangular box with
Yeah, okay.
no bound on the right. You can fit all your toys in this toy box and then some.
Well, it's only 4 high, so like, what if I have a toy that's like 5 wide,
Lay it down.
but it's a cube?
No, it's not. That end is unbounded.
And you cut off the top and put it side by
It's
side.
not a cube.
My toy though is bigger than the, like it's infinite box this big, so my
What if
toy
your
is.
Damn, you got an infinite box toy?
You have strange toys.
And it's filled entirely with Legos.
Just,
An infinite box of Legos.
There's your Riemann sum right there.
that's my dream as a child.
Wonderful. But like,
Probably all are engineers.
well, do you have to like keep on like digging around for the right piece?
Oh, yeah. Imagine how messy it would get.
They're not sorted, that's all. Yeah. Well, so Legos that are not, you'd have to go through an infinite regression to the next sort.
Yes, it's an awful idea, okay?
Yeah, so don't sort them, it's better to have them random, because
No,
you have a
even
higher
if
chance of reaching.
No, you
So
don't
there's
look
so
for the
many
right.
So too much thought. What is going on with the train of thought? I got too much Legos. What? Okay, what are your thoughts about this one? I've got x times e to the negative x, and I'm integrating from 0 to infinity. So the 0 part's okay. E to the minus x is continuous, the product of these two continuous functions is continuous. It's the upper limit that's makes this improper.
We need to do an integration by parts.
You are gonna have to do an integration by parts.
Really?
You probably never have to do it again now that we're out of that section.
I was hoping we wouldn't.
So use integration by parts.
I kind of just saw it as, hey, look at this cool thing, we'll never do it again. But
You were wrong.
I was
You were
wrong.
very
Oh
wrong.
my gosh, your first week of differential equations, you're gonna do them all again too.
Oh, nice.
Joke's on you, I'm dropping out before that.
Taking that.
Not an I.
I don't think I do, but I'm
Hey,
also
Travis,
gonna
can you hit
get
my
it
ear,
math.
Travis didn't hear it.
Wait, are you, you're integrating by parts, concentrate. Let that Adderall kick in.
You wrote it backwards. What did you say?
You wrote which one backwards? He's top one. He's lower. He's never-
Yeah, that's where the advisor pretty much forced you to say, okay, start with one, you can figure it out later. And then tried to force you into the same path everyone else was. No matter how
It's
much
important
credit
not only that you recognize integration by parts, but that you can also do it.
I recognize integration by parts.
I recognize the name.
I can do integration by parts.
Good.
Seems-
That's
it
why when
seems
everybody
a
says,
little
I
bit
can do integration by
Seems
parts.
like I've seen this before.
There's a difference between can and want to.
Circular integration by parts?
No, this one's a one-stepper.
Do you take U?
Is it?
U is x and dv is the e to the negative x.
Like your first week of Calc 1 and they like teach you like coordinate thing.
I don't know if I got
And
that
it
correct,
like
but I'm gonna roll.
sucks and then they just.
What's the integral of e to the minus x?
Negative e to the negative x.
There you go.
Okay, I may have got it right.
All right, so we want a uv minus the integral of v du over there. So uv is minus x e to the negative x minus the integral of v, which is e to the minus x dx. And I put the minus sign out front. I'll worry about the 0 to n in a second.
Well, we're gonna end up changing that plus sign to a minus sign.
Yep.
Wonderful.
Excuse me. And we want the limit as n goes to infinity. Are you okay with the antiderivative? Minus x e to the negative x minus e to the negative x?
That's what I got.
Okay, maybe,
Yeah.
and make sure you're using it properly. Minus n, e to the minus n, minus e to the minus n. Minus, this is gonna be 0, minus e to the 0. What's e to the 0?
I know
So that
that
back
one.
thing back there is gonna give me a 1. What about this one? E to the minus infinity is the way that's gonna behave. E to the minus infinity is 0. So I get a +1 out here. So this is what we're worried about here. And so this is infinity times 0. That's an indeterminate form. So what's a quick way to put it in the proper form for L'Hopital's rule?
Negative n over e to the n.
And over.
Take a look at the negative exponent, put it on the bottom.
Yeah.
And so now it looks like infinity over infinity, and you can do L'Hopital's rule. Okay. So you take the derivative of the top, divide it by the derivative of the bottom, and then attempt to do the limit. What do you get out of that limit right there?
0.
That will be 0. So I have 0 plus 0 plus 1.
Hey.
So our integral converges.
I have a question.
Yes,
Are you gonna be going over something that's gonna completely change my conception of calculus for the next problem?
man, I take that as a challenge.
I need to pee.
Hey.
Like, right now, I'm asking you, is now the time in the movie where I need to
Where the bus.
Yeah, go to the restroom. Anybody else have bladder issues before I do the really cool example?
Class break.
So now I gotta find a less than cool example while he's relieving himself.
Oh, we should just like take a break.
We should all just leave and start doing math outside.
Turn the lights on.
Yeah, try like break out and like go here.
Yeah, and what if you just write some calc 3 on there?
Yeah.
And then we all pretend like we're following along.
Oh, yeah.
Please. Please don't write some really fancy calc 3. That will make me put a 5 on your.
I'm not.
She doesn't need a
I'm not
5.
bad.
She already has a 5.
She has a 4.9. We can make it a 5. I'll offset that. If you get enough 5s, it rounds off.
That's an approximation.
Yeah, but alternatively, we can just lock it in.
Or we could do that.
Back to do it.
Knock off the trash. Trash can.
You do it.
You're closer.
You're taller.
What does that have to do with knocking trash cans over?
You take longer steps, so it takes less time for you to get over
I
there.
guarantee you get there
You can
faster.
probably just pull it out from where you're sitting right now.
That's what
I
we'll
mean-
do.
I'll take it as a challenge.
But we have to stall, because this is the really cool example. For one, what makes it really, really
Damn, that looks
cool?
like arcane. That is.
We're definitely your favorite class.
Is that true?
What's that?
What were your favorite class?
You're my favorite class.
Your favorite class from 10:30 to 11:45.
10:30 to 11.
Don't cut ourselves.
Just to 11.
Just to 11.
The last 45 minutes.
Just 30 minutes.
Your favorite class for however long Logan's in the bathroom.
Wait, what if we all move chairs right now?
We're not doing a change, sorry.
Okay, shuffle.
Still all his stuff.
All right, I'm sitting here now.
All right.
Where should I go?
I'll flip to the front row.
Where should I go?
All right.
Go in the back.
Top.
Back to any
I don't think.
Like the very back?
Is that his?
No, we, but you want to move to?
I'm right here. Mine's all set. I'm just gonna go to the very, very back. No one's even gonna steal his actual chair.
Would you like me to? No, I'm doing it. All right.
Y'all might wanna hurry, it's been taking a while.
Wait. Also.
Very nice.
You gotta be like this.
You wanna throw this stuff over? Yeah, get back to work.
Just like hide it. That's somewhere weird. Put that like up here.
Yeah.
Yeah, we're so productive.
Hey, man, come on, Jackson.
Why are you blaming me?
Because you're always one that moves.
I'm not even in your seat.
Like we always
What
want
the
them.
hell? I don't wanna sit in the corner.
We ate your homework.
No.
Oh, wait. Is this the cool example? Yeah.
This is a cool example, there's more. But this is big time improper.
We were in a
because
rush.
Both limits of the interval, you need to fix both of them.
This is still for the type A, right?
Yep.
Or type
Type
1.
one.
Type A indefinite integral.
So what we've got to do to fix this is split it up somewhere in between. So how about at 0? So we made one improper integral into two improper integrals. It's buy one, get one free. But now we fix both of these improper integrals. I'm gonna write this as, I don't know, let's use different letters. Let's put an M down here. I'm gonna let M go to minus infinity. And then I'll put an N up there, and I'm gonna let N go to positive infinity. So we're able to fix them with limits so that we can apply the fundamental theorem of calculus. We can evaluate their antiderivatives at M, 0, and N, and then let both M and N go their infinite little ways. So what's the antiderivative of 1 over x squared plus 4? 1/2 arctangent of x over 2. 1/2 arctangent of x over 2. Right? Integral 1 over a squared plus x squared dx is 1 over a arctangent of x over a. So our a is 2. So I get 1 over 2 arctangent of x over 2. And I have to evaluate this one from m to 0. And then let m fly off to minus infinity. And we're going to let n go to infinity. Oops, arctangent 1/2 arctangent of x over 2 from 0 to n. So I'm going to put the 0 in there and the m. So I'll do it right here. X is 0. We have the arctangent of x. And the arctangent of m over 2. Then I have to add 2. I'm factoring out the half so I don't have to write that twice. I need the 1/2 arctangent n divided by 2 minus the arctangent of 0. I was hoping somebody would tell me what the arctangent of 0 was.
0.
Because
Oh, it is 0.
tangent of 0 is 0, so the inverse tangent of 0 is 0.
Perhaps it doesn't matter.
So these are both gonna be, oops, this meant to be 0 here.
Arctan of infinity.
That's my next question. This goes to minus infinity, this goes to plus infinity.
Do they cancel? 3 pi over 2.
No, the n and the m. So what do you know about the graph of the arctangent function?
It's
It goes.
Now the tangent goes zoop,
Oh, okay.
right? Think of your tangent curve, it has asymptotes where?
At
Tangent of x,
one
tangent of x.
and negative one. Wait.
Pi over 2. Tangent is sine over cosine, cosine of pi over 2 is 0. So one period of the tangent function, one period of the tangent function looks like this. That's minus pi over 2. There's pi over 2. Tangent of 0 is 0. It looks like that. So if I ask you to draw me the graph of the arctangent function, the y's become the x's become the y's. So if I'm drawing the graph of the arctangent function, the vertical asymptotes become horizontal asymptotes. This is y is equal to pi over 2. This is y is equal to negative pi over 2. Tangent is 0 is 0, inverse tangent is 0 is 0. They both pass through the origin. What's the inverse tangent of say 1? What's the arctangent of 1? It's pi over 4. What's the arctangent of negative 1? Negative pi over 4. So fake the rest of the graph.
So it's infinite
What is?
as it approaches infinity and
Let's
negative
put
infinity.
n out here and let n go to infinity. What does that n?
It's
What's the
gonna
graph
be
doing?
infinity because the
Pi over
behavior's
2.
not asymptotic.
It is having.
It is.
Wait,
It
no,
is.
no, no.
Pi
It is pi over 2.
It's going to pi over 2. And what about as m goes to minus infinity?
Negative pi over 2.
It's going to negative pi over 2.
So would they cancel out?
Let's see.
Infinity minus infinity.
This is,
Pars or minus.
I get, that's going to be 0. This one was going to be pi over 2. This 2 doesn't matter, does it?
No,
M goes to minus pi over 2. Right, and then plus. That one's gonna go to, oh, I've got the 1/2 out front. Let's put a 1/2 out here. N goes to infinity, this goes to positive pi over 2. And that goes to 0. So this first batch here is going to become pi over 4. Second batch is pi over 4. So this thing all adds up to 2 pi over 4 or pi over 2. So it converges. Let me show you what the graph of this thing looks like. That thing looks something like this. Symmetry about the origin. Something like that. Where have you seen a curve like that?
Bell curves.
It's bell curve. Where do they play a role? Probability and statistics. And a normal distribution, you can take this type of thing here from minus infinity to infinity and scale it in such a way that the total area under the curve is 1. And then it represents a probability density function associated with a normal distribution. And then you can box off different pieces of area to represent probabilities that a normal distribution takes on numbers between those values. So I've scaled it off so that the total area is pi halves. So it looks like I'd have to multiply this whole integral by 2 over pi to make that into a density function. That was pretty darn cool, huh?
That is pretty cool.
All right, we'll take this out of there and put our, what did we just integrate? X e to the negative x, is that the one I want? Right. Let's make it easier. Let's go.
We have to do that one.
Let's do this one.
So first line, should we start?
I don't want to integrate by parts, so I'll just fix that. Is that an easier integral than the one that was the integration by parts?
Yes, thank you.
Because
You.
it's just a u integral. But because both limits on the integral sign are infinite, we've got to break that up around some point in between. Doesn't have to be smack dab in between, but zero is a convenient enough point. So start the same way by integrating from minus infinity to 0 of x e to the negative x squared. And then integrate from 0 to plus infinity of x e to the negative x squared. And then replace the infinite limits with letters and make limits out of those integrals. So I'll write it just the way I did a minute ago with an m for the lower limit. And an n for the upper limit, let n go to plus infinity. So we're going to kind of crank it into gear. Let's go ahead and compute the antiderivative aside, and then we'll put the bounds in. You said that was a u du integral. How did you recognize that?
Power of x squared e to x is greater.
The exponent has one power more than the x in front, so that's a u du integral.
Does it matter if we make it a negative, like,
Oh, it doesn't matter to me, as long as you're able to compute it. I'll do it aside here and I'll go back and fill it in over there. We take u to be the exponent. Du negative 2x dx, or negative 1/2 du is x dx. So this becomes negative 1/2 integral of e to the u du. Quick, what's the integral of e to the u?
Du.
There we go.
I practice my flashcards every night.
I only do it in the shower.
Laminated flashcards.
Yes.
That's how I know the shower's over. My flashcards are gone. Okay, so I'm going to put that here. E to the negative x squared times the negative 1/2. But the limit as m goes to minus infinity. So minus 1/2, 0 is going to go in first. So e to the minus 0 squared. And then minus e to the negative m squared. And over here, got a minus 1/2, ooh. And then n, e to the negative n squared minus e to the 0 again. So what are your thoughts? Okay, 1. What happens here?
0.
That's gonna be 0. That's the same as saying, right? So if I take a big negative number and square it, it's a big positive number. E to a big positive number is big. Divide that into 1, and that's 0. So this is going to 0 here. So I get a negative 1/2 out of this. Over here, same deal. This term is going to go to 0. and this goes to 1, so -1/2 times a -1 gives me a +1/2. This integral converges to 0. That one probably does something like this, I'm not sure, but probably does some version of this. Yeah, I'll screw. The negative area and the positive area cancel each other out. Okay, that's the end of our integration and our integration techniques. I'll talk a little bit, I'll introduce you to hyperbolic functions. I'm not gonna actually cover hyperbolic functions, I just want you to know they exist.
Sure.